So coefficient moles and volume. So when we have 1 mole of nitrogen and 3 moles, 1, 2, 3, of hydrogen, we already know that it makes 2 moles of NH3. Now, the strange thing about these gases is that even though I have more volume on the left, you can have different volumes on the left and the right because we're making something that's kind of tighter, like a tighter little molecule. It doesn't have to take up as much volume. So we have this relationship right here. In the same container, we know that the volumes are proportional. So do you see how this is 1 volume of N2 are proportional to 3 volumes of H2, and it's proportional to 2 volumes of NH3. So the volume could be anything. We're going to pick a useful unit for the ratio, and usually it's just easier with gases, like up here, to use this liters ratio. It's easier to do a liters ratio. So here's one ratio, and here's another ratio. These are meaning the same thing. So let's see this in action. All right, so here's the long way to solve this problem. Nitrogen reacts with oxygen to form dinitrogen pentoxide. Here's the reaction over here, it's balanced. What volume of oxygen is required to produce this much of him? So we're producing this, and it wants to know how much oxygen is going to be required. Notice that we have a temperature, and we have a pressure, and we have a volume. So the long way, again, is to begin with what you know, which is that dinitrogen pentoxide. Divide both sides by RT. And we can take the numbers from the problem. So we have our pressure, which is 1 atm. We have our 12.6, our 12.5, which is our liters. Our 0.0821, you know all about that one. And here is our Kelvin value. So all that's from the problem. All the problem numbers are in there. When you put you in your calculator, you're going to 1.53 moles of that. Then, like before, you're going to have to do 1.53 moles. You're going to use that molar ratio. So again, the 2 to the 5. And you're going to end up with moles of oxygen. It doesn't want to know moles of oxygen. It wants to know the volume of oxygen. So guess what? Now you get to plug that into another PV equals nRT. This PV equals nRT was for 2 to 5. This PV nRT is for oxygen. It's rearranged solving for that. And you can see here is where it goes in. That's your normal R, there's your temperature, and there's your ATMs. Now see, if it was a container and it was just holding all of it, if it gives you these values for one gas, it's also the value for the other gas because they all are in that same container. And then we get this answer right here. That's using the PV equals nRT equation twice and using a molar conversion. Is there a faster way? Oh, yes. So we're going to use the volume relationship that we were just talking about up here. So our volume relationship is that we have 2 liters of N2 that are proportional to 5 liters of O2 that are proportional to 2 liters of N2O5. So we'll take our 12.5 liters, and this is 12.5 liters of the dinitrogen pentoxide. And we're going to say that in 2 liters of dinitrogen pentoxide, we have 5 liters of O2. You do the math on that, you're going to end up with 31.2 liters of O2. Wow, that was a lot less math.